number. Okay, next time, 4. For all the assignment, don't send the electronic file to TA. You have to print out and bring it to me in class, okay? I know assignment one, I asked you just send the electronic file. That's because of what? Because of the holiday of the national anniversary. But don't make it a regular, okay, activity, okay? I need to print out. I know it's a kind of a West, but please print it single-sided on each page. Don't print it double-sided, okay? Now, this time it's okay, but because sometimes maybe I need to write something. So give me some empty space so that I can, if I need to write something for you, okay? I know this will save us a lot of papers, but just make it single-sided. 单面印，不要双面印，好吧？因为老师有时候会写东西。But you do need to read my remark. Don't just repeat the same error. Because I just got the assignment too, but based on my experience, you just keep writing your own style and ignore my comment. For example, for the figures of table, I asked you need to make the figures number, and you need the caption. And you need the table number and the title for each table. Please do that, okay? 就是习惯你有时候你表也不编号啊，也不写这个表是在做什么，这个图是在做什么。I mean, you need it for your thesis, anyway, for your final thesis. So make it formal, even though it's only an assignment. Okay, make it a habit. Okay, let's say today we will finish. Remember last week we talked about dilation, which means to grow, right? To grow. Erosion, opening, and closing. Okay? We apply this for morphological operations on a digital image. With that, I know we can use this process for region filling. Okay, this case, okay, if we have only some boundary, okay, we want to fill the inner region with the same color, okay? So after that, you will fill this. And this is the structural element you use, okay, across here. Okay, I won't give you the detail, just take a look. So you need a process, okay? The morphological 1, 2, K means the case morphological operation, okay? So it cannot do it in just one single morphology. So X0 means the original, okay? The original. original boundary. Okay, then we do the dilation because you want to fill the empty space within a contour. Okay, then we take the intersect with the complement of A. Okay, the complement of A. It means the complement of A. Okay, that's it. So if this is, then if this is A, okay, this is the input, which is the boundary, and this will be the complement of A. See that? So what I mean is 0 becomes 1 and 1 becomes 0. Okay, so that's it. Okay, that's it. This is so-called complement. And we keep the same process for many, many times until there's no changes at all. Okay, if k minus, which means if k equal to xk minus 1 iteration, which means there's nothing else to fill. It means the operation is completed. Okay, then we stop. So this is the process for region filling. Okay, and you can also apply this for leveling. Remember the leveling? I show you the example like this, right? It started from 1, right? And then 2, right? And this could be 2 or 3, blah, blah, blah. Okay, so this so-called leveling. Okay, the operation a little bit similar to the region filling. Again, we need the iteration 1, 2, 3, and so on. Okay, x0 is the original binary image. Then we carry out, okay, because you want to do the leveling, so we go for dilation with some structure element. Then we take the intersection with A. Okay, so starting x0 is just a point. Okay, just like the filling here. Okay, initially x0 is a P, which is a boundary point. It's a point inside the boundary. It can be any point. Okay, you can pick up any point inside the boundary. Then for leveling, the same here. You're starting from a point. Okay, it's a point. Then we do the dilation and intersect. Okay, with A, and we just repeat the process. Then you can, and finally, and everything will have the same level. Okay, so that's another way for the extraction of connected component. Okay, I believe OpenCV will provide these operations. Okay, this is the structuring element. Okay, structural element with the origin or the center in the middle, right here. Okay, then we can starting from any object point. Then we start to fill. Okay, that's it. Okay, this for level. And also you can do the skeleton. Okay, do the skeleton. Something like this. Okay, if we have an object Y, after the operation, this will be the final. This will be the final. The skeleton. Okay, final skeleton. Then the size, well, at the end, you will have something like this. Not just, you might have just something like this. Okay, at the end, you will see only the skeleton. But for this case, you may see something more right here. Okay. Then that depends on what is the radius, okay, or the size of your structuring element. 你就会看到很多小细节的话，那是跟你的 structural element 有关的哈，你选的有关。你选的越细的话，它这边就会它就会有很多小枝节就会出来啊。比较大的话，对不起啊，它比较小的话，你看它这边可能东西就不见了啊，就这样。Okay, skeleton. Okay, a little bit complicated, but just follow the procedure. I'm not going to say anything more. Okay, but you need to repeat it. Okay, you need to repeat it for different K. Okay, K means K success erosion. Now it goes to the erosion. Why erosion? Because you try to find the skeleton, right? Just find the skeleton. 因为它要找的是它的 skeleton 嘛，所以一定要缩，就缩，这个很可以。像刚才你要把中间的部分涂同一颜色，或是你要 level， 当然就是一定要去找嘛，从一个点开始，就这样。Okay, so then SK is nothing but what? Is erosion. This is the original, okay? And K is the success erosion of A. So we apply K's structural element and do the subtraction, okay? Okay, and this is the opening operation. So this is the procedure, okay? This is the procedure for skeleton. So this will be another example here. We have a binary image. Apparently, it is a horse, right? So after the skeleton, you can see something. Just see the skeleton, okay, of the original object. But you know some of the point might be disappeared, okay? That's something you must keep in mind when you try to apply morphological skeleton. For this case, somehow some of the fine detail is gone. So you may need to do some post processing to connect the broken edges. OK， 好，这是你做完以后，有些东西可能会不见了哦，这个要小心。好，不过基本上他就在做这件事情，我们只把他的 skeleton 找出来啊，我们只找他的 skeleton。好，它的骨架，它的骨骼 ，OK， so that's some of the application, not all the application, okay, for morphological function in a binary image. Okay, now we are going to extend the morphological operation from binary, okay, from binary to now we are going to for gray value or grayscale image. And the same here, we have four basic, actually again, two basic operations. Dilation, erosion, okay? And then we can extend the dilation, erosion with some of the combination for opening and close. It's the same here for gray value images. But the definition will be a little bit different. Okay, so let's take a look. 好，所以等一下我们谈这个 morphology， 直接在灰阶影像里面做。Okay, we applied it. Okay, here's the definition. Okay, here's the definition. The dilation. Here's the dilation. Okay, no matter for two-dimensional or one-dimensional, it'll be fine. For one-dimensional, usually we are working this for time series signal, okay? 1D. You can apply the morphology, the same operation here, okay, to the one-dimensional, For smoothing, you might have something like this for smoothing, okay, or for sharpening. You can do a lot of things here, okay? This is the general case. Okay, let's back to the definition of two-dimensional. It's nothing but just we pick up the maximum. That's it, okay? So the dilation we simply pick up if I is the image, this is most of the case we apply the dilation. Okay? Which means you pick up the local max. Let's say we just pick up a local max. And the local or the neighborhood is defined by the structuring element, just like the binary morphology. So again, you can define your own, okay, structural element, the shape, the size. But most of the cases, we simply use a 3x3 or 5x5, okay? But sometimes you can use a horizontal, okay, summation. It can be 3x3, okay? As I mentioned, you apply dilation twice with 3x3 structural element is equivalent to one, the dilation with one 5x5 structuring element. Okay, so usually we go for this, or we might go for the crosshair or horizontal structural element or a vertical structural element. That's it. Okay, that's the most of the case. But you need to define, for some case, it cannot be 3x3. Okay, it got to be a 1x5 or larger. Okay, but anyway, this is the more general definition, which means you can change the graph value. Okay, when you assign the structural element, not just the shape or the size. For example, you can put 10 here, for example, and put just 5 on the diagonal element. Okay, you can put something here, and then you can change the value for this definition here, and then you can change the value. But most of the case, because you know nothing, what should be the value? No, it's too complicated. You know what I'm saying? 你又不知道你要把它放大多少干嘛 So most of the case, we simply use the structural element to define the shape, okay, and the size. That's it. We don't change the value, okay? We don't change the value, the graph value. We don't change it. But anyway, for dilation, in a binary image, which means we try to expand, right, to grow. But in graph level, if you apply dilation to an image, what could be the result? The image will becomes
very large.
You won't change the image. The image size will be the same. But however, every value, okay, here's every value, x, y, the original value. You just look, this is the original value. Then you find its neighbor. You find its neighbor defined by structural element and pick up the largest one. So in the end, the image will getting brighter, right? 会更亮，一定会更亮，只会更亮。But the age, you will blur the ages because everything will getting brighter, right? So you will lose a lot of details, but you are getting brighter. So anyway, just keep that in mind. Usually we don't assign the value to the structural element since you don't know what should be the value, right? For each element. Now we don't. Now, if this is easy for you, then you can imagine it. Now you know how to define the erosion. If dilation is make the image brighter, then erosion will make the image what?
Darker.
Right, definitely you look for the minimum, okay? In the region defined by the structuring element, that's it, okay? Again, for all the neighborhood, okay? When I say ij, okay? When I say ij here, in the center, it has the coordinate, okay? 0, 0, okay? And this one, well, -1, 0, okay? And this is 1, 0, and so on, okay? Well, what about opening? What about the opening? Here, the opening here, the same here, okay? We do the erosion first, and then followed by dilation. So which means we make the image darker, and then bring it back. Okay, we bring it back, make it brighter. That's called opening, okay? And then, you know, the closing, it got to be, we make it brighter, okay, first. And then try to find the minimum, which means we do the, you can think of this as a kind of a mini-max, right? I'm sorry. I should say max min. Right? We find the minimum first, and then try to find the maximum next. Right? So we go for the max min. And for the closing, then we carry out maxima first, and then minima next, in a local region defined by the structuring element. Okay, so again, it's very important to define the shape, define the size, okay, of the structuring element. Okay, so that's it. Okay, that's all you need to know. But you can do a lot of things for you. Okay, it's simple, but it's very, still very powerful. Okay, so that's the only 4 operations that you need to keep in mind. Okay, any questions so far? Okay, if don't, I'll show you some example and some application for graph value. Okay, morphology. 事实上它的定义也是只有这4个，就这4个呢，在这边的排列组合。That's it. Okay. Actually, this should be our next topic when we talk about the age detection. Okay, but since we're talking about the graph level morphology, so here's a function called morphological gradient. Gradient means the difference, right? The gradient, T2. Okay, gradient. Because we are talking about 2-dimensional, so we use a gradient. If 1-dimensional, we talk about the derivative. 微分嘛，实际上就是微分微分 the difference, okay? If you don't like this word, but we use a lot the gradient, okay? The gradient, morphological gradient. You can find the edges of the object, okay? It does not have to be a binary object. Can be any object in the grade level image. 它可以找物体的边缘点，在灰阶以下不是二质化以下。Okay, so morphological gradient is based on the first derivative. Okay, it's based on the first. Of course, when we talk about the gradient, you will find the gradient. Okay, along the x-axis and the y-axis， 也就是它会找水平跟垂直。这个是我们等一下要讨论的。Okay. Now, let's take a look how it could work. Again, you need to define the structure element. If you have no idea at all, just go for 3x3. Okay, just go for 3x3. Unless you just want to identify what. If you have a structure element like this, okay, then you are looking for what? The vertical vertical line, right? Right? Because you need to, this is the image. Then if this is your structural element with the center right here, then you have slide this structural element pixel by pixel, right?
Yeah.
Then eventually you will look for a vertical line. That's it. If you care only about horizontal line, maybe you need to go for this one. Okay, that's it. So most of the case we simply apply a 3x3 or 5x5 to identify all possible edges. Now, the definition is like this. We find the erosion. What is, I'm sorry. First, define the structural element. Then we carry out dilation. So what is the value? Local max, right? Dilation here. Try to find the local max. So this is the local max. Then we apply the same structural element again, but we find the local minimum. So this is the difference between the maxima and minimum. Definitely Z is non-negative because we find the, so in what case, if we have an object like this, okay, if we have an object like this, and we apply a 3x3 structuring element, and this is A, what would happen here? If we put B here, the maxima is basically the maxima, local maxima is equal to the local minima, right? 因为你放在这边嘛，它找最大最小不都一样吗？ So the value, the gradient will be very close to 0. Okay? If we put the structural element inside the object, the result will be the same because the local maxima is almost identical with the local minimum. So only when you put the structural element around the edges, then it will show you the local the local minima and local maxima will be quite different. So this value will be very large, which indicates xy is an H point. That's the idea. So this is the gradient because it's based on the very first derivative, the first degree difference. You see that? The difference here. Okay? The maxima minus minima. So the morphology gradient is equal to the local max minus local minimum. Okay, it's based on the first derivative. 它是利用一阶微分最大减最小。Okay, so it means the dilation and minus erosion. Okay, that's the so-called gradient. The result will show you the edges. Okay, the edges. That's it. Here we have another two very important operation used in graph value image by morphology. One is called top hat. Okay, one is called top hat. The other one called bottom hat. Also known as, okay, just write it down, called black hat. Because in OpenCV, you can find the function called top hat, but you cannot find the name called bottom hat, but you can find the name called black. I don't know why, okay? I think this could be better because right, the bottom is opposite to top. But anyway, okay, the bottom hat okay, is the same as the black hat function in OpenCV 啊 ，OpenCV 它用 black hat， 你不要说我要去找 button hat， 如果找不到，自己写，自己写没有什么了不起了啊 ，OK。Now take a look. Basically, the top hat transformation is using for light, which means for bright object on a dark background. Okay? I didn't say you can only apply this to this kinds of image, but most of the time we applied it to a bright object on the dark background. Okay? And button hat or black hat, it do the reverse way is for dark object on a bright background. Okay? Now here's how it works. A is the original image. Okay? Remember, A is the original image. Now we carry out we take the minimum and then maximum. Okay, we take the minimum and then we try to find the erosion. Okay, right? We try to find the dark, and then find the bright one and subtract it. Okay, and subtract it. Okay. And for button hat, it goes the reverse way because this value will not larger than the original graph value. 也就是你这边哈，因为你先找最小的，然后再找最大的话，这个值呢还是不会比它原来的更大。Okay, because we take the minimum first and find the maximum in the neighborhood. So the resulting value will not be larger than the original graph value. So we put A minus here. Okay? But for button hat, we take the maximum first, and then we try to find the minimum based on the maximum result. So the value will be definitely larger than the original graph value. So we minus A. So no matter it's for top hat or bottom hat, it try to find what? The difference, the main difference in the original image. So this could be applied used for defect detection in manufacturing to find the defect. Okay, you know what I'm saying? Because if the original image contains some, if you have something like this and you have a defect, you can remove something. Especially you can remove, for example, you can remove the vertical background. Okay, and then you try to, when you get the subtraction, then eventually you might just preserve the local defect. So the defect detection from the top hat or bottom hat will be much easier to identify the local defect from the original image, okay, with a complicated background. Okay, so that could be one of the applications for that. Okay, sometimes, especially, I put a remark here. Okay, if you go for the top hat transformation, I'll give you an example. It will correct the effect of non-uniform or uneven illumination, because sometimes you have when you go home, you can make a trial. If you just take a look, okay, the white sheet of paper here. If I use my fingernail, okay, I put a scratch. Okay, well, from your distance to the paper here, you cannot see nothing. But when you go home, when you rotate the paper at some very particular angle, you can see this scratch, fingernail scratch. Okay. Don't laugh. Don't say nobody is going to do that. Well, actually, if you have a chance to visit the LCD manufacturer, You know what I'm saying about LCD, right?
Yeah.
Liquid crystal display, 液晶显示面板. What is the size now? The TV set you use at home?
TVs,
I mean, now the most popular size could be 50 or 65 inches. It's very huge. Do you know how the inspector tried to find this kinds of, the so-called Mura defect? That's because the defect is caused by the liquid, crystal liquid. Okay, a lot of. They use a machine, a very large machine, and they try to rotate the LCD. And the inspector stands right in front of the machine, and hopefully at some very particular angle, then you can visualize this. That's how it goes. Okay, but anyway, that's another story. How to make it automatic, but still.
it's still manual in this time, right?
Yeah. Yeah.
Why don't they apply the automation? Is
Because it's very, very difficult. Just what I'm saying here, you cannot see. Mura in Japanese is very close to blemish of the light. I mean, it will cause the visual uncomfortable. But in not when you go see the movie or something, you cannot find the details different. But if you look very closely, you can see some spot here. A bird. It's not just what I'm saying here. I meant a scratch. I can make a scratch, but at very particular angle, you can see this defect. Okay, so. Anyway, that's another story. So remember this, top half and bottom half, okay? We do the closing and subtract it from the original one, or we do the black half and subtract the original image. Now let me show you this application here, okay? This is the original image. This is a dilation. Okay, we use a square, okay, structural element such as a 3x3. So see that the white object is getting larger, right? See that? Okay, no problem. It's getting larger. Okay, and when we do the erosion with the same structural element, see that the object becomes thinner. Okay, because our background is dark, right? So the erosion, we try to find the minimum, right? So if we use a very large structural element, what would happen here for this one? If we use a very, very large erosion, if the size is larger than the width of the object, then it will become what? A black, a very dark image. That's it. You won't see anything, right? Right? And again, if you use a very, very large structural element and you apply to the image here, then everything will become white, okay, or very bright, and you cannot see the image. So it's very important to select a good structuring element, okay? That's something you need to learn here, okay? Now, this one is we carry out closing. Okay, we carry out closing, and this one we carry out open, so that the size are maintained. See that? They are almost the same. Okay, the size are almost the same, but you can see a little bit difference compared with the original one. At least you can see something. See that? We have two isolated objects here. They are connected. Okay, they are connected. Okay. Now, this is the gradient. This is the gradient. Okay, this is the gradient. So you see only about the edges of the object, right? How come I didn't have a Laplace? Do I have a Laplacian operation here? Oh, right here. Okay, I skipped the morphology Laplacian. Basically, you try to emphasize also the edges, but based on the second derivative. Okay, so here's the equation. We do the dilation in -8, so that's the gradient. See that? The first term here is the gradient, right? And the second term, we A minus erosion, okay, the minimum. And then we do the subtraction one more time. See that? So this, you can think of this, the first term here or the second term here as a first degree derivative or the gradient, okay, of the gradient. But the subtraction of the gradient, see that? The subtraction of the gradient, you can think of that as the second derivative, okay? 好，这是二阶微分，二阶微分就是一阶微分再微分，就是算它的差，两个之间的差，OK？ 可是呢，这边都减掉 a 啊，那除以1/2是因为我们把它的剩一半 ，OK？ So this is much easier. So Laplacian is also trying to emphasize the edges. Okay, so we can base on gradient or based on the Laplacian to identify the edges, and this is the result here. Okay, so this is the gradient. Based on the gradient, this is based on the second degree Laplacian. Okay, you can see a little bit of the difference here. See that? Okay. Then this is the top hat. From the screen here, you can visualize the difference. Actually, this area, okay, you have an uneven illuminated background. I don't know if you can find it from your printout or something, or go back, take a look at the screen. 事实上这边会比较偏暗 ，OK， 这边会偏暗。But after the top hat, it will remove the uneven illumination in the background. It will make the background or make the lighting more uniform. Okay? 这边看不太。Can you see the little bit difference here? See, it's brighter here. See that? So obviously the light source, okay, it's come from the upper left corner, okay? So when this corner is far away from the light source, it's getting dark. So 你注意看一下，这边比较亮，背景。I talked about the background. It's brighter, but it's darker here. But after the top hat, basically you cannot see the difference, right, in the background. Okay, so that it makes the illumination more uniform. Okay, that's one of the purpose of top hat. Of course, you can apply what would happen if you use black hat or something else. Okay, it's a very useful tool. Okay, for pre-processing or post-processing. For binary image or for ground level image. Okay. And I give you one more, which is not a standard operation, but some paper. Simply we talk about the sharpening, right? Remember we talk about you can use here. F is the original image, okay? So F plus means we try to find the local max, okay, dilation. And F minus is local minimum. Now we change the graph value like this, okay? We will change the value, this xy, I should put a parenthesis here, okay? The original image will change it to F plus, okay, or F minus, or we don't change anything. So if F plus, the local max minus the original value is less than the original value minus f minus. Otherwise, we put it f minus, which we return the minimum. Okay, you may not understand why is that, but when we take a look, we think of the one-dimensional situation here. Suppose f is the original curve, okay? And this one is the result of dilation. We try the local max, right? Local max. This is dilation. And this is the local erosion. We try to find the minimum. And this terms here is just the result for here. So it means what? We make the subtraction. We just take any value here. Suppose we take a value. Let me make it, draw the line. If this is the local max, and then we have a local minimum. Okay, this is local minimum. Then we try to find, for some value here, we simply calculate the value, this distance, and this distance. So apparently this value is much closer to maximum. Agree? Right. This is the local max. And this value is a local minimum. If the distance to local max is much closer to the distance to local minimum, of course, I assign this value to a local max. So if it should be a brighter, I make it more brighter. And for this one here, if this point should be darker, right? Compare with the local max, I change it, I make it dark. See that? If it's brighter, I make it more brighter. If it's dark, I make it more dark. That's it. That's it. Okay? That's the idea. So this is the final result. See that? It kind of we try to sharp the edges. We'll sharp the edges. So this is one of the application. Okay? This is the original. Okay? This is the blueprint. Okay? 蓝图了, blueprint. Okay, this is the original. You can still read the digit 5.6 something. This is the line, a very thick line, very thin line. And this is the dilation, okay? And this is the erosion. It is getting darker, right? Then this is the sharpening. See that? I mean, can you tell the difference, right? The line is sharpened now, okay? That's the result. That's something you can write. It's not a standard operation you can find from OpenCV or any library, but I mean, it's quite simple because you can still apply what? You can use OpenCV, right, for dilation, erosion, and you just write these conditional branches. That will be good enough, okay, for sharpening, okay, for sharpening. Okay, let's take a break. 那个确定作业都交了吗？
还是要等一下。
我要等一下。
我也忘记在实验室了。好。